All right, roots of swarm intelligence. Where did it come from? Well, when Jim Kennedy and I started working on this, Jim is a social psychologist, and we were working in areas of flocking and swarming and schooling. Birds flock, bees swarm, fish school, how are societies modeled, and what's artificial life? And we don't get into that in this presentation, but that's one side of where we came from to build this. I came from the side of engineering and computer science and working in something called evolutionary computation, and this area is part of an evolutionary computation application, which is related to evolution, although they're not in any way biologically related. So, I'm going to talk about three basic social psychology areas that contributed directly to our swarm work. One from a guy named Bibb Latané, Axelrod, some people have heard of, some haven't, and then Jim Kennedy's adaptive culture model. Okay, Bibb Latané, actually Jim Kennedy he was Jim Kennedy's major professor in North Carolina, and a very famous guy in social psychology, and he had some theories on social impact, and one of them was that people's behaviors can be explained in something called self-organizing properties of their social system. Self-organizing is something that happens when something bigger than the sum of the parts occurs. And one example you're all familiar with is the water temperature goes down below freezing, ice crystals start to form. They come across and we get a layer of ice, and that's an example of self-organization that occurs. Another example is the development of the human brain after we're born. It develops in a process we call self-organization. Latané also talked about how clusters of individuals, groups of people develop similar beliefs. We all experience that. The people we spend time with, we tend to assimilate the same beliefs as the people we spend time with. However, we also get polarization. I run around with one group, somebody else runs around with somebody else, and we get subpopulations that diverge from one another. These all were factors in what we were doing. So characteristics here, as people are exposed to majority arguments, sometimes diversity is reduced. This occurs, we're watching a political campaign now with people trying to get you over to their belief with majority arguments. But at the same time, people are becoming more like their neighbors in social space, and clusters are forming. And attitudes that were originally independent tend to become associated together. So people tend to find people with beliefs that are kind of similar to theirs and then correlate. However, this clustering prevents small groups, all the groups, from all getting brought into one cluster. So that in summary, individuals influence one another. When they do that, they become more similar. The patterns of belief held by individuals tend to correlate within a population, and this can be in societies primarily. And we see this in a number of these fields, sociology, anthropology, and so on. Now comes Axelrod. Latané was 50 years ago. Axelrod, in fact, is fairly well known in computer science, so those of you who've been around that may have heard of him. But he's the first one who ever represented populations of individuals as strings of symbols in a computer. So he took attributes of people and put them into computers as strings. And he talked about interaction between people, a culture model, where the probability that any two of these individuals would interact would be a function of how similar they are. Do they share attributes together? And as a result, the individuals become more similar as a result of the interactions, but that last bullet says the dynamic is polarization. So these groups form, but they then tend to cluster and differ from one another. Jim Kennedy took that a little bit further in what's called Kennedy's adaptive culture model. In looking at how to model his social systems on a computer, he said he didn't want there to be any effect of similarity on the probability of interaction. What he wanted to implement was the fact that dissimilarity would create the boundaries between the clusters, the social region. And interaction occurs if fitnesses are different. All right, here's a new concept called fitnesses, central concept of what we do. Anytime we try to solve a problem, we're trying to increase the fitness. So the definition says it's a value assigned to an individual, it's a possible solution, and it reflects how well these systems that have populations of individuals, we calculate or somehow determine fitnesses for them, and that's the value, that's how well that individual is solving the task. So in summary here, for culture and cognition, individuals that look for solutions are learning from experiences of others, and that individuals learn from their neighbors is the key to swarm intelligence. That is probably the one phrase that best characterizes swarm intelligence. Individuals learn from their neighbors. If you look at a population, you look at things that are happening of which the individuals are parts, and the individuals that interact most often become more similar. The culture affects how these individuals perform that are within it, and the individuals typically gain benefit or get higher fitnesses. They're able to do their job better because they imitate their neighbor. So what about intelligence? Well, what we say, and particularly Kennedy says, social behavior like this increases the ability of an individual to adapt or to do things that are useful. There's a relationship between this adaptability and intelligence. And the last bullet is still a little bit controversial, but it's becoming more and more accepted. And Jim Kennedy was the first, or at least one of the very first, to propose that intelligence arises from interactions among individuals. I won't go into it in detail, but basically Kennedy's hypothesis is if there's no interaction, there's no intelligence. And he cites examples of feral humans, humans who were never in contact with another living human being. We don't find very many of them anymore, but they find a 12-year-old kid that's been in a cave, has never been in contact with other human beings, and that 12-year-old had no attributes of what we call intelligence. Intelligence as measured, let's say, on an intelligence quotient test or an IQ test. So intelligence as defined by intelligence IQ test, Kennedy says arises totally really from interactions among individuals. Well, there are various types, ways of looking at this. One that we based our work on, one branch of it, flocks, herds, and schools, and we note that bird flocks, they may split, but they it shows a flock here splitting around used to have a pole drawn in there, around an obstacle, but they steer toward the center, they match their neighbor's velocity, they avoid collisions, and sometimes they seek a roost or they look for food, that kind of thing, but they act together as a flock. And bees swarm, and here some other people whose work we based our stuff on. Jim Kennedy calls this coherence without choreography, and I think that's a good way to describe a bee swarm. The difference with our computer swarms, our particle swarms, is that physical position isn't a factor. As you can see here, bees can collide, and birds can collide, and fish can collide, but our stuff in our computer, our particles, cannot collide, even though they look a lot like some of these swarms. So what is swarm intelligence? A couple of attributes of it here. I have a couple of slides that talk at this subject. Collective adaptation behavior of a population of simple entities that interact either directly or indirectly. That means we have a population of when it says simple entities, it means not smart necessarily. They're not necessarily autonomous in the sense that they are totally independent, but they are typically much more simple than that, and all they really know is where they are, how well their solution is, and they know something about some of their neighbors around them. Simple entities, but they can solve very rapidly very complex problems, converge or cluster in a many-dimensional and dynamic problem space.